cannot pool them, you will do an unpooled variance t-test, otherwise known as Welch-Sathert weight. On the other hand, let's say that I had this scenario. N1 equals 40, S1 equals 3, X bar equals 89, and N2 equals 30, S2 equals 2.75, and Y bar equals 94. All the numbers are the same except for him. So F naught test statistic in this case would be the larger S squared divided by the smaller S squared. What does that come out to be? Can you get me a number? You squared them?
Yeah.
Yeah. I got 1.19. Yeah.
1.19?
Yep.
1.19. So that one does not fall in the rejection region. All this will be the same. F, 39, 29, and I really should cancel that, right? And make it 30 and 29 because the 39 didn't exist on the table, remember? And everything else is the same. This is still 2.092, but this time I fall here. F naught equals 1.19. And therefore here, the conclusion will be do not reject H naught. That means assume that the variances are the same. And do a pooled variance t-test. Are you with me? That's the first procedure you have to do before you can do any t-test. When you see S's for independent samples. Okay. So let me teach you how to do the pooled variance t-test right now. So coming back to this test here, I have to make some modifications to that. So let's begin here on page 3. I started with Z naught equals X bar minus Y bar minus mu X minus mu Y divided by rad sigma X squared over NX plus sigma Y squared over NY. This is what it used to be. So I'm starting to make some changes now. Change this to T naught. And we're assuming that the sigmas are the same. So on the bottom, can I go like this? Radical sigma squared. I'm going to pull this sigma out because I'm assuming that sigma x equals sigma y equals some common sigma, right? Because I'm pooling them. I'm assuming that the variances are the same. So radical sigma squared times 1 over nx plus 1 over ny. All I've done is factor out this common sigma squared. And then I realized that I don't even have sigma squared. They didn't give me sigma squared. They gave me s's. So I'll go like this. Of course, square root of sigma squared is just sigma. Rad 1 over nx plus 1 over ny. But I don't have sigma. So I need an estimate of this sigma. which is going to be called SP, P for pooled. So this estimate is going to be SP. I have to find SP. That's a standard deviation, the pooled estimate of the standard deviation. So turns out that SP square is equal to nx minus 1 sx square plus ny minus 1 sy square over nx plus ny minus 2. So what's happening here? Let's understand what's going on here. This is a weighted average of the two variances that were given to me initially. They gave me standard deviation so I can find variance, right? This is a weighted average for these two sample variances, and I'm weighting by the degrees of freedom. These guys are just the degrees of freedoms. Degrees of freedom, and let me write it. Degrees of freedom. And on the bottom is just nx plus minus 1 plus ny minus 1. So that's how I got that, nx plus ny minus 2. So it's a weighted average. So where is this coming from? Let's just back it up a little bit. You remember this formula? S squared is equal to summation xi minus x bar square over n minus 1. You remember this formula for variance from before the first exam? If I took the square root, I would get s, right? That was the formula for the standard deviation. I'm using this, but I'm cross multiplying. So let's call this sx squared, and let's cross multiply nx minus 1. Go like that. Couldn't I say that summation xi minus x bar square is equal to nx minus 1 sx square? That would be a fair statement. All I did was cross multiply. I do the same thing on the other side. Sy square equals summation, summation yi minus y bar square over ny minus 1. Cross multiply there. So let me write that. ny minus 1 sy square equals summation yi minus y bar square. Now I'm pooling all of this, right? I want one value of the pooled variance, SP square. So why not take all of these plus all of these and lump them together? So I'm going to take the deviations that come from the x's, xi minus x bar squared. These are the deviations for x. And I have a whole bunch of them. And then I have a whole bunch of deviations for y, yi minus y bar square. And I'm interested in the sum of these. I'm interested in sum of xi minus x bar square plus sum of yi minus y bar square. I want to lump all of these together. So that's where I get nx minus 1 sx square. That's this plus that, which is ny minus 1 sy square. And then I'm going to divide that by the sum of this and this. And that's how I got this formula. Are you understanding me? So to find the variance is defined as the mean of the square of the deviations, right? So I took all the squared deviations for x, and I took all the squared deviations for y. I added them up, and I divided by nx plus ny minus 2. Because it's dividing by nx minus 1 plus ny minus 1. And that's where this formula came from, SP squared. So it's not SP squared that I'm interested in. I'm interested in SP. So once I find this, I will find the square root and stick it in here in the denominator. So when all is said and done, it's T naught equals x bar minus y bar minus mu x minus mu y. This comes from the null hypothesis. Oh, you can't see what I'm writing. That's the test statistic. Divided by SP square root of 1 over nx plus 1 over ny. That's the test statistic for the pooled variance procedure, where SP is given by that formula that we just found right here. SP is given by this formula, where SP equals that. Actually, SP squared is given by that, and SP equals square root of SP squared. I'm anxious to do an example so you can see it done. Page 4. I'll go and do this example right here. So, example 1. Oh, good. So we already decided that we were going to do a pooled variance, right? Because look where the F test statistic fell. It fell in here, meaning do not reject H naught, where H naught said that sigma 1 square equals sigma 2 square. So I actually want to finish this problem up and do a pooled variance procedure on this problem. So example 1, pooled variance. Let's say I'm testing to see if mu x minus mu y equals 0 versus HA mu x minus mu y less than 0. Let's say it's left-sided t-test. So here's T with nx plus ny minus 2 degrees of freedom. The total degrees of freedom is nx minus 1 plus ny minus 1. So when I add those, I get nx plus ny minus 2. It's the same exact number as the denominator of this SP square. This is the degrees of freedom for my t-test, pooled variance t-test. You're with me, right? So in my case, it would be nx plus ny minus 2 is equal to 39 plus 29, which is 68. So this would be done at T 68 degrees of freedom. And it's left-sided, so put your entire alpha in the left tail. So alpha equals 0.05, goes in the left tail. Here's 0. After all, this is a t distribution, so this critical value is going to be negative. Let's go to the t table and look up 0.05 column for 68 degrees of freedom. So here's t. .05 column is here, and 68 degrees of freedom. Now I don't see 68, but I do see 60, and that number is given by 1.671. Agree? Except it's going to be negative because it's on the left side. Minus 1.671, and let me